Hi everybody, welcome back to the channel. In this video we're going to talk about a new idea, or at least a new way to see derivatives. Now that we've been working with derivatives for a little while now, and we know some different rules about how to handle different functions, we're going to see a different way to look at the topic. We actually have one more family of functions left to look at when it comes to derivative rules and understanding how families of functions behave. We haven't looked at logarithms yet, so that's still coming up. But other than that, logarithms are our last family of functions that we're going to look at. And in order to be able to figure out how logs behave, we need to see a derivative differently. But not just to see logarithms, we also need to see a derivative a little bit differently for other reasons as well. Every function that we've seen so far has looked like y equals something, or f of x equals something. And every function that we've looked at so far, or every equation that we've looked at so far, has been just that. It's been a function. The problem with that is that when you have other graphs, I'll use a pretty straightforward example as a circle. This is not a function, but we should still be able to pick a point on the circle and say, what is the slope of the tangent line at a specific point? And we shouldn't need our graph to be a function. We shouldn't need our equation to start out looking like y equals. So what if we have an equation that has a bunch of different x's and y's in it? That would be a relation between two variables, but it wouldn't be a function. So for example, x squared plus y squared equals 4. This doesn't just look like y equals something. Now I realize you could solve for y in this equation. You'd actually end up getting two different equations, because when you take a square root to get y by itself, you'd need a plus or a minus in there. So you end up having two different equations, but we have much more complicated equations that have x's and y's in them, and we don't necessarily have to only be talking about functions. So we need to be able to kind of expand our view of a derivative to be able to talk about any kind of a graph and look at the slope of the tangent line at a particular point using a value of x and a value of y. Here's how we're going to do that. Let's start out with a pretty basic equation. Start out with something like y equals 2x squared plus 4. And if I asked you to find the derivative, you should feel very comfortable with this by now. But I could actually rewrite this same exact equation in a little bit of a different way. For example, it's perfectly fine for me to write this equation as 2x squared minus y plus 4 equals 0. Not a problem. And that way we have all of our x's and y's all on one side. And so if I said take the derivative and find y prime, find the derivative of y, you could either start at the beginning and just take the derivative of y, or take the derivative of this equation, and you'd get y prime all by itself. What you're actually doing there, though, instead of just saying take the derivative, really what you're doing is you're taking the derivative of both sides. Here's what that looks like. Let's say you start out with a y equals 2x squared plus 4. When I say find the derivative of that function, what you're really doing is this. You're saying d over dx of y and d over dx of 2x squared plus 4. Okay, so you're actually taking the derivative of both sides of the equation. It's kind of like saying square both sides or multiply both sides by 5. You're taking the derivative of both sides of the equation. But on the left side, there's not really much to do. We would just write y prime or dy dx, either way. And then we'd say, well, what's the derivative of 2x squared plus 4 on the right side? Well, that's just 4x. And so, but what we're doing there is taking the derivative of both sides of the equation. We can do that regardless of whether it starts out as y equals, or whether we have an equation like this that starts out as 0 equals 2x squared minus y plus 4. Let's say you take the derivative of both sides of the equation there. That would look like d over dx of 0 equals d over dx of the entire right side, and you have 2x squared minus y plus 4 inside. And then we know that when you take the derivative of a sum or a difference, you can just kind of take the derivative of each of the terms there individually. But when you take the derivative of 2x squared, because it's with respect to x, that just kind of works the same way we'd always known it is, and we get 4x. But when you take the derivative of something with a y in it, right here with this minus y, it's not just minus 1. Like if this was a minus x in the middle, the derivative of minus x would just be minus 1. But the derivative of minus y isn't just minus 1, because when you talk about taking the derivative of y, another way to write that is dy over dx, and you have something different on the top and on the bottom, a dy and a dx. If you had something like a negative x in there, and you'd say take dx over dx, okay, notice you have the same thing on top, dx, as you do on the bottom. That's just 1. You could say, oh, you have the same thing on top and bottom, those cancel. That doesn't happen when you have a minus y in there, so you need to leave it as a minus y prime, or you could say y dy dx. Those both mean the same exact thing. And then plus 0, and on the left side, the derivative of 0 is still the derivative of a constant. You could add y prime over here to the other side and get 4x. We already knew you should get 4x. But the idea here is that regardless of where y is, you can go ahead and take the derivative of both sides of an equation and take the derivative of each of the terms there separately. And everywhere you see a derivative of something with a y, you're going to not just have the normal derivative like you're thinking. You would need that to be a dy dx or a y prime. Okay, so let's go ahead and look at, we're going to look at a few different examples of how to do this. And we've talked about a lot of derivatives rules so far, and we still need to keep those in mind. Those are all going to show up. So I want to just look individually at one term for a second before we look at this term showing up in an equation. So what happens if you're taking d over dx of y squared? That's what we just saw, that a y squared showed up in the equation for a circle. And we're going to deal with that here in a second. But what does d over dx of y squared look like? Okay, so I'm going to write this just a little bit differently. Keep this in mind. Remember, y is a function in terms of x. So y has x as the input. You can write that in this way, and it means exactly the same thing. Y of x squared, okay? Or maybe I should put the square in the middle just so we know that the square is on the y. So something like d over dx of y squared of x, okay? And so another way to write this, if I wanted to kind of keep in mind outside functions and inside functions, is that this is like saying take y of x and square it. So what happens when we take the derivative of something like y squared? Well, this is actually a chain rule here. Okay, think about y, think about something squared as being like the f on the outside. So I'll kind of use the notation we had in the last video. And then the g, or the inside function, is really like your y of x. Okay, so think about an outside function and an inside function. What does the derivative of this look like? It actually looks like taking the derivative of something squared, which is 2 times something, and then multiply by the derivative of that inside something. So what was inside of the squared? Well, it was just a y, or you could say y of x, and that's fine. And then we need to multiply by a dy dx, which is the derivative of the inside, or you could call that y prime as well, that's fine. And so when we take the derivative of y squared, we actually end up getting 2y, and this part right here is really like your f prime of g part from the chain rule, and then multiply by the derivative of what's inside, multiply by the g prime, which is like a y prime for us here. Okay, so why does that matter? How is that going to change things for us? Let's take a look at the circle example that we had earlier. And let's suppose that we have an equation like x squared plus y squared equals 4. Okay, this is a circle that's centered at the origin, that has a radius of 2, but definitely is not a function. Okay, and what we want to do is we want to find, here's kind of going to be the directions for this whole section. You could say find y prime, or probably more likely we're going to see the notation find dy dx. And you know those mean the same thing now. Hopefully we've done enough practice with those that you're comfortable with either of these notations. That's my hope. If you're not at this point comfortable with both of those notations, I would say go practice as much as you can, as quickly as you can, because we really want to be comfortable with both of those notations inside and out. Okay, so what does it look like to find y prime or to find dy dx? We're going to have a y prime in the midst of our problem, but then we're going to do some algebra to get y prime all by itself and solve for y prime. Here's what this is going to look like in this problem. Take the derivative of both sides. So d over dx of x squared plus y squared, and then d over dx of 4. Okay, let's start with the right side. That's a little more simple. The derivative of a constant, of any constant, is 0. Regardless of what variable you're taking the derivative with respect to. So regardless of what's on the bottom, even though we've pretty much only seen dx on the bottom at this point, the derivative of a constant is still just 0. All right, now the derivative of x squared is 2x. It behaves just like we would have thought it does because x is the variable that's in that term, and we're taking the derivative with respect to x. Now, what about the y squared? Well, that's what we just did earlier. That's supposed to be 2y times y prime, or you could write it as dy dx. Again, I'm using both notations, even interchangeably. Like in one step I wrote d over dx, next step I wrote y prime. If you would like to be consistent and kind of pick one, that's perfectly fine. I think it's probably going to be more common in these problems in this section to write dy over dx like this, but as long as you know that you could have written y prime there, and I would be perfectly fine with that either way. So this is your derivative of 2x gives you, or the derivative of x squared gives you 2x. The derivative of y squared is a chain rule, and this is again like your f prime of g part, and then this is like your g prime part, and so that's what we have. But notice the directions say find dy dx, get that all by itself. So now do some algebra to solve for this piece and move everything else over to the other side. So we're going to have something like 2y times dy dx equals negative 2x. Go ahead and move that 2x over to the other side. And now get dy dx all by itself. These are being multiplied, so divide by 2y. So dy dx now is equal to negative 2x over 2y. And the 2's can cancel, and you actually end up getting dy over dx equals negative x over y. And there we got dy dx all by itself. So just like when we talked about a function and when we took the derivative, we still had an x left over in the equation. In this one, because this is not a function, we actually don't just have an x in the ending equation, we actually also have a y left over in there as well. And kind of a quick graphical explanation of that is because your circle here, it doesn't, the slope of your tangent line doesn't just depend on what x value you have, it actually also depends on what y value you're dealing with on the graph as well. So for example, let's say you have a point on the graph like this point right here. It's not just based on its x value, because this point down here actually has exactly the same x value. So if all you knew was an x value and you wanted to find the slope of the tangent line, you'd have to ask the question, wait, which tangent line am I looking for? There's two of them and they definitely have different slopes. Which one am I talking about? So that's why there's a y in that equation, is the y helps us distinguish which of those 2 points are we talking about. You wouldn't have that with a function because this wouldn't pass the vertical line test. But with this gives us the opportunity to talk about all sorts of graphs, even if they're not functions, anything that's a relation that involves x and y.